In this video, we'll talk about the sample impulse modulation first. Alright, and therefore let's remove the whole. Alright, this part, I'll just simply remove it, same as its corresponding graph. Alright, if you were to zoom in, this thing is actually your analog signal, your continuous signal in the time domain, or in the time domain. Alright, and you're going to modulate it, impulse modulation. So when you take different points to sample, these are all points over here. Alright, the impulse modulations is just taking impulse at this point, and then taking another impulse at this point, taking another impulse at this point. So therefore you have so many lines over here. Okay, that's what I mean just now. Alright, so how does this equation works? Is that your time function, which is this one, alright, is RT. Okay, a summation of all your sampling in terms of an impulse, so it's an impulse sampling. Alright, so at time t, so what do I mean is that when time is equals to 0, your delta is equals to 1. Alright, so therefore you shoot up as 1. So this is your time is equals to 0, right? So this is 0, this is 1, 2, over here. Okay, so if time is not 0, delta is equals to 0. So therefore when time is equals to 0, you will have some form of like that, but you cannot see here. Alright, but how does this KT come in? If you still remember, this KT is just simply the shifting. Alright, so if T minus KT, alright, KT can be this KT, can be this KT, depends on the K you're talking about. Alright, if it's 1T, this means that you have one period. So maybe if your graph is something like this, one period is over here. Is it? Wait or something like that okay? So one period is somewhere over here. So instead of this point over here now, alright, your impulse will shoot up. So when your T is equals to so when T minus KT, alright, when K is equals to 1, as I say, alright, so it's just one period. So T minus 1 period is equals to 0, meaning you're taking, instead of, maybe I should remove this point explicitly. So I'll remove this point already, so it's not here anymore. Alright, so it's over here now, I mean here. So this is the new point, your T minus tau. When your T minus tau is equals to 0, delta is equals to 1, so it shoot up. Alright, and then when T minus tau is not equals to 0, delta is equals to 0. Alright, and therefore at this point in somewhere, maybe another period, maybe somewhere over here, then it's like that. Then okay, how do I say? Then what about those points in the middle? So you can vary your K. Your K is divided, so one period is 2 pi. Alright, so K you can divide maybe like 1/2, 1/4, 1/5 of the 2 pi. So you dissect your 2 pi into many parts. Maybe this is the one, I think you get what I mean already okay? If K is equals to half, maybe this is 2 pi, right? So if K is equals to half, then half times 2 pi is equals to pi. So you're taking this point over here. Alright, and then if it's quarter, then it's a half pi. So you're taking this point over here. So 1/8 pi, you're taking all these points over here. So this is how you take the rest of the points in such of a manner. Alright, but at least you get to see that you're taking each of the impulses at each of the points and each of the K that you subs in. Alright, hopefully this is pretty clear. Therefore I repeat again, this function over here describes your analog signal. Alright, while this one over here describes how you take each of the points from the analog signal by using impulses, taking each of this point over here. Alright, that's all it means. Alright, and by block diagram graphically, alright, if you have a certain RT transfer function, I mean certain RT time domain, something of that describe this curvature over here. Alright, this is the equation. You go through your impulse system or your period or whatever, you will have all this. You're gonna impulse modulation, and this is what we call this this sampling method, we call this the impulse modulation. Alright, so now I'll simply take this thing, because I don't want to cheat your feeling. I take all this thing, I put it over here. Okay, so this thing is this thing. And double check, I didn't cheat your feeling. Okay, and this page over here is simply the page that you're you are given in your slides over here in these slides. Alright, just crop it out only. Okay, and then I'll just simply shift a bit so at least it doesn't corrupt your understanding. Alright, so this should be the case over here. Right, this should be fine. Okay, so this thing over here, maybe hold on a while. Aha, we have this already. Alright, just simply rearranging only for better sake. So this thing over here, when I want to Laplace transform, a Laplace transform means that you're going to transform a certain function with this red color one that I've just drawn. Alright, why the circle always hold? Anyway, this over here, all these things are the Laplace transform, the red color one. Okay, so we're going to transform this function. Same thing, we're going to transform this function. Alright, bring it all over here. So you double check, this thing over here is same as this thing, while this thing over here is this thing. So it's simply Laplacing. I mean, you're gonna Laplace transform your stuff. That's all it is. Alright, so when you Laplace transform, alright, instead of t now, we sub in as tau. Okay, we do it as tau. It's telling people that, dude, we are going to Laplace. That's tau, something like that. But anyway, I don't know why you want to do that. Okay, so now, in order to cut short, because since we know that this portion over here is your 1, alright, you know that this is the impulse modulation, alright, but in the time domain, alright, in the time domain, this is simply just some conditions telling you when t equals, in this case is tau, so when tau is equals to 0, delta is equals to 1, when tau is not equals to 0, delta is equals to 0, alright, things like that. So it's just telling you the conditions. So therefore, when you Laplace transform your this thing over here, alright, like this. So this thing over here is simply, wait okay, so he simply actually shortcut also. So del tau or del minus kt, alright, simply the same because it's just a shifting. We have proved to you, right? Because if you have tau over here, for example, if tau is equals to 0, this is 0. If tau is equals to if tau is equals to 0, delta is equals to 0. However, we can also say that when tau minus kt is equals to 0, alright, delta is equals to, what am I talking? When tau is equals to 0, delta is equals to 1, and therefore it's over here. So far so good? Now, if tau minus kt is equals to 0, tau is equals to 1. So tau minus kt, this is kt, alright, is equals to 1 over here. Then the rest are all zeros. Alright, so it's simply talking about the same thing. But this is just a some form of a general equation for this thing over here. Tau or tau minus kt, they are the same. So this whole thing over here, when you Laplace, this thing over here is your Dirac delta function. Alright, so you Laplace transform your Dirac delta function is equals to 1. That's just the meaning. You can also Laplace del tau minus kt, you're equals to 1 also. If you were to Laplace it, like infinity minus whatever, and then e minus st over here, you still get back this thing. I mean, it equals to 1. Alright? Or something of the variations. I don't go through that, but at least that's the meaning of trying to prove to you. Alright, and therefore, since we know that this thing over here is just simply 1, so 1 times r tau, alright, with to be more exact, is that summation of all the r tau, or r tau. So summation of all the r tau times 1 is equals to r star tau. Or in other words, it's simply rewriting this whole chunk here, okay, as r star tau. Alright, knowing that this thing is 1. So this whole summation times 1 is simply r star tau, that's all. Alright, while the rest, the e minus s tau is brought over here, your whatever is continued. Alright, we haven't Laplace transformed yet. Alright, but at least you get to see how it's being derived up to here. Okay? Next, because we are going to do integration by parts, I see this as a very troublesome thing. I'll not go and do integration by parts. But once you integrate this thing over here, alright, where you know that r star tau is this chunk, hopefully this one, because this is still 1. But anyway, once you Laplace transform already, because take note that there's one tau over here and there's another tau over here, that's why it's like a product rule. So product rule, you need to integration by parts, right? Yeah, I hope you get what I mean. And therefore, if you integration by parts, you eventually get something like this. Alright, where you switch your tau, instead of tau you switch it to kt for some reason. Alright, so I'll not go into details on how to switch here and there, but at least you get a feel that this impulse modulation is simply to modulate, or in other words, you have all this little thing. If it's whatever, how do I say, you're summing out all this thing. At first, when k is equals to 0 sorry, when k is equals to 0, you create this point. Alright, when k is equals to 1, alright, you have this point, although it's not exceptionally correct because it's in terms of a period. So if it's period, something like this. Alright, so if it's k equals to 1, the next point is kt, which is 1t. The next one coming out where k equals to 2 is 2t. So you are taking all this. If you are taking more sampling points, meaning when k is equals to maybe half, so half t is somewhere over here. Alright, and you're gonna take all these things over here. If it's like a 2t and things like that. So you're getting, so if your k is more sensitive, meaning you're dissecting your this curve to more points. Alright, so you're going to take all this modulation, you're going to take impulse over here, this impulse. So the summation point is to sum up all these points to, so each of the section over here, normally when k is equals to 1, for example, you take 1 point only. Okay, when k is equals to 2, you take another point. K equals to 3, you take another point. Then when you summon up all together, you're just simply displaying all the points. And that's all it is. I hope that this is pretty clear for you. And r star t, alright, you will become r star s, capital R star s. For example, if you have yt, right, you Laplace transform it. Normally people write it as capital YS. Same thing. So this is a small capital R star. So when you Laplace transform, become capital R star. Alright, and these are the few stuff that I just want to convey to you. And I hope that this meaning is fairly useful to you in the future. So see you soon. I mean in the next video.